Renee Huinker. I am findable on Twitter at DataRenee, and I am here today to talk to you about a talk titled No Array of Sunshine, a data quality focused tour of data types. And what I want you to know is, and this is the big takeaway, is that this is a talk about how choices we make around data types can impact data quality. Data types can take your data from fledgling chick to a majestic eagle or a French fry hunting seagull. So before we embark on this talk, the first thing that we all need to agree on is what is data. And the first thing about data is that it is pieces of information with a format. Another thing to think about is that it is facts used for making decisions. We can also consider data to be information stored in and or used by a computer and a representation of some aspect of the world. So now that we've agreed on some ways that we can think about what data is, we want to think about what makes data good. And for me, that means that data needs to be fit for its intended uses in operations, planning, or decision making. So why do we want to have good data? Well, like we said earlier, planning and operations. We also want to look smart. We want to save money. Like we said, we want to make decisions. And for today's database joke, we want to complete transactions. So in order to assess data quality, we're thinking again about, is it fit for its intended use in operations, planning, and decision making? And we'll think about 6 different aspects of data. And going through them one by one, we want to know, is this set of data complete? And by that we mean, are there gaps between the expected data and the data that we have? And do we have enough data for the task at hand? So to make the plan, to answer the question, to complete an operation. A second aspect of data is uniqueness. Are there any duplicates in the set? And is each item represented only once? So whether that's something that might look like a duplicate, where you've got 2 people who have the exact same name, because those are 2 different people, those aren't truly duplicates. But if you have one person whose name is spelled 2 different ways, that would be a duplicate. A third thing to think about with data quality is timeliness. Is there more recent data that can help us do the task at hand? And is the data accessible in a way that's fast enough to allow us to answer that question or make that plan in the time that we need to accomplish this? Another aspect is validity, thinking about the format, the syntax, and the type of the data. So as we know that this is a talk about data types, so validity is going to be very important. And we want to know, could this data even potentially be accurate? Is this data within a range that we expect? And are there any surprise null values? Accuracy, we want to think about, have we stored the correct value? And we also want to think about whether we've chosen the correct units of measurement. For units of measurement, an example of this might be if we have 10 cups of flour, do we want to be measuring that out in teaspoons, or do we want to be representing it as cups? Consistency. Do we have conflicts between our data sources and within our data storage? Another aspect of consistency is the question of, does the database only change data in expected ways? So while we won't be thinking about all of these aspects of data in today's talk, we do want to know that they exist. Additionally, we want to think about the data funnel, how it comes to us. And we won't be thinking about every part of the data funnel in today's talk with our limited time today, but we do want to be aware that the data funnel comes to us beginning with acquisition and data entry, so how we got the data and how it got into the computer. And then we want to think about cleaning and transforming data, how we store the data, what is our process for analyzing the data, And how are we going to use that data to make a profit, whether that profit is earning more money or saving time? We'll need to be aware during today's talk that we do have broadly two kinds of data. Quantitative data are things that can be easily expressed as a number: distances, weights, counts, and time. And qualitative data is used to think about things that you can't easily express as a number. This would be things like color, mood, reason, or opinion. Today, we're going to be focusing on quantitative data, again, because we do have limited time. So, a very easy way to think about quantitative data is as a number. So first, we're going to take a look at storing numbers, and then we're going to look at math with numbers and how data types can affect both of those. First, like we said, storage. Robert Treat has given a talk on the int to big int conversion that he has come across in some situations. And he describes this problem of integer to big integer conversion as Goldilocks and the three data types. And when we look at the Postgres documentation of data types, specifically in this page, numeric data types, the very first one is small int, the second one is integer, and the third is big int. And in the second column, you can see storage is a concern. The smallest int, called small int, takes up 2 bytes and has a limited range. The highest number stored can be about 32,000, maybe getting up near 33,000. And so that range goes into the negative up to the positive. Integer can hold about 4 billion items because you've got negative 2 billion-ish on the low end and positive 2 billion-ish on the high end. And that takes about twice as much storage per item that you're hanging on to. Big int now takes further double what integer takes to store. So many organizations decide that we aren't going to need 4 billion things. And also most organizations start at 0. So from 0 to 2 billion, we don't need to store 2 billion things. So we're going to go with integer because that's as big as we could possibly need it to be. And then they're thinking primarily about storage, that 2 bytes to 4 bytes to 8 bytes. Well, we know we need more than 32,000, so let's go in the middle. Hence Robert Treat's Goldilocks. Here is some bigger font of the upper range boundary of these three data types. 2 billion is a very big number, and I don't even know how to say that very, very, very wow large number at the bottom. It's really big, and it can be inconceivable to most people that you could ever need a number that big. Why spend all that money to store something that you can't conceive of needing? A very relevant question for most organizations. So what happens, though, is an organization can run out of usable numbers before running out of things to count. This is especially true in industries like banking, where you have millions of financial transactions a minute. You can see how you could very, very quickly get up to 2 billion. You also may be aware that some social networks have millions to billions of users and are having millions of messages a day, millions of pieces of data a minute or a second that they're having to deal with. So what happens when you run into the situation where you have run out of numbers is you get an error or you don't get an error, and you then need to change all of your 2 billion records that you have in the integer type over to the big integer type to allow your big integer type to take over. What happens when you have to make a change like this is that you end up spending a lot of time and a lot of money to accommodate this change that you need to make. And this is very unpleasant. So what may feel like a savings at the beginning of setting up and into the middle, and just before you get to the place where you have a problem that you need to solve, can actually turn out to be an incredibly uncomfortable and expensive problem. So that is a very brief tour of how storing numbers can cause you problems, because if you aren't getting your data into the database because the integer is out of range, then you can't use that data that's not in your database to make any decisions. And so what you have with missing data in that incompleteness area is bad data. The next thing we want to think about with data quality and numbers is math, particularly with integers. We call this integer math, and we can see that we're using here integer. We could use small int and big int for these math problems as well, never fear. But we're going to also look at decimal and numeric as different. Well, we're actually only going to look at integer and numeric as ways to do math here. So let's say I have 80 customers and 75 of them really, really love us. And I want to know what percentage of our customers really, really love us. I would say, give me the column of customers that really love us divided by the column of customers that we asked. So I would divide 75 by 80. And if I didn't realize that I had stored both of those numbers as integers, I might be very surprised when I see that the answer is 0. How is it that 0% of our customers love us? I need to talk to customer service very fast and find out why our customers are so upset. So just knowing what data type you have can help you with these problems. But if you're not familiar that integer math causes problems or causes answers like this, you might start to wonder if perhaps your computer has forgotten how to do math. So now we can take a look at what we call data type casting. So we've still stored our 75 in the database as integer, but we're casting it now to numeric to do that division. And when we do numeric division, the computer is kind enough to do a whole lot of precision for us. And what we're most concerned about is accuracy. So we don't necessarily need 10 or 15 zeros at the end of our division result. So the next step with integer math is to take a look at rounding. Tell the computer how many spaces of precision do you want. And in this case, what we've chosen is 3. We can see that approximately 94%, but very specifically 93.8% of our customers are very happy with us. And that is much more comfortable for us as an answer. We can also do that same math with with casting to a decimal. So we can cast to a numeric or a decimal, and there are very interesting cases for why you would choose both or why you would choose one or the other, and that is out of the scope for what we're talking about today. Another thing that we'll want to look at is Boolean values. Yes and no are what we think of when we think about Boolean, but it's very easy also to think about maybe. And what I want to talk about specifically today is choosing other data types rather than the Boolean data type. It turns out that some people have not yet learned of the magic of the Boolean data type. So it's not unheard of to meet a company where they've used a text field or a numeric field to serve the purpose of a Boolean. And what happens when we do this, we can give you an example of creating a table that we'll call test, and we're going to give it 3 different columns. And the TF in this case stands for true, false. So column number 1, I'm calling true, false text, and I've given it a text type, varying character. My next column, I'm calling true, false, Boolean, and I've given it the type Boolean, which we now all know about. And then the third column that we're creating here is called true false integer, and we'll make that an integer. Here's what happens when we insert into our table. We can have y, y, and 1 to represent true for all of these. And I want to point out that the text column will accept literally any text we give it in this case. The Boolean column, this is not on the slide, but we should know that Boolean will accept yes, no, y, n, t, f, true, and false, as well as null. So y and t can both be capitalized. All of the single letters can be capitalized. And the true and false and yes and no can also all be capitalized or lower cases. The database doesn't understand, doesn't care that there is a distinction in this case. And so all of the y's, t's, and trues and yeses will resolve. How do you think? Well, I've just told you they're all going to come back as true. In the integer column, we can see that the ones all correspond to the trues. And then in our text columns, I've done something silly with, in our final row, I have done something silly with the text and the numeric columns and given values that aren't going to resolve to null or unknown. I've given the number 4 and the word maybe. So when we ask the computer, tell me everything that was in the table that we called test, you can see it's returning back 4 lowercase t's, even though we remember that we gave it a y, a t, a true, and a yes. So it knows that we meant that all of those were true. We can also see that my maybe and my 4 have come through exactly as we entered them into the computer. So now I want to show me everything where I have said that this is true. This gives us every row back minus the row where I said null, because null is not true. So as we can see here, when we select everything from this table where the text is true, it only returns us the row where the text was literally true, even though we have several Boolean fields that we know resolve to true. So all of our other true options, the y, the t, the true, and the yes, get lost. With this in mind, it's really important to keep track of, in this specific case, using a Boolean field instead of the other fields that may be tempting to use because you think that you might be able to convince your users to only enter true, or you feel like the data source that you are receiving is reliably formatted in a very specific way. It's very easy in a lot of databases to ingest text as text and leave it as text, even when that field was intended to be a Boolean field and is currently all as Boolean. Treat it as Boolean, because if you run this query on a text field, it will return incorrectly. But if you run it on a Boolean field, it will count up the number of trues that you truly had. With that, I want to thank you all for coming on this very brief tour of data types and how they can affect your data quality. I really appreciate you taking the time to join us today.